All right, so our next speaker is going to be Doyoon Lee from Seoul National University. He's going to be talking about how we can accelerate sketch style synthesis by figuring out how to fill in the holes more intelligently. With that, take it away, please.
Let me start. Hello, I'm Doyoon Lee from South Korea, and I'll introduce my work titled Inductive Program Synthesis by Meta-Analysis Guided Hole Filling. Co-work with Professor Woosuk Lee and Professor Kwangkeun. So let me first introduce what is inductive program synthesis is. There is input-output pairs given and also grammar constraints given. So the goal is to find the program which satisfies all input-output pairs. In this case, we can find two solutions and whatever okay when it is fine. And the problem is the exponentially growing search space. So we use bidirectional program synthesis algorithm, filling bottom-up components into top-down templates to make big program sketches in early stages. So here comes the hole. The hole means currently not filled but grow into any program. And now we can see example partial programs here. While doing bidirectional program synthesis, we pick components and put into holes. So there will be partial programs with holes. When we see this, 2 times 2 plus 4, we should satisfy those input-output pairs, but we can find out that output numbers are odd. So is it feasible? Actually, no. We can analyze this by abstract interpretation, especially forward and backward interpretation both. The forward analysis will give whole as a top and whole times 2 as even. And backward analysis will give, we know output 3 is odd number and plus 4 will be minus 4, so there's whole times 2 as odd. So we have two constraints with whole times 2, forward, even, backward, odd. By meeting two constraints, it will result in both. So we can result whole times 2 plus 4 is infeasible for IO pair. Now here comes our observation. Hole filling order matters. In existing synthesizers, they doesn't consider real about hole filling matter just using left to right filling. But let's see this example. When we use left to right filling, 11 candidates explode. And when we use the right to left filling, we explode only 9 candidates. Because in real case, there will be more components and deep sketches. This difference will be exploded in exponential way. So we found it out that we can find preferred order in dynamic way for each situation. Let me take my idea by some analogy. Think about your racer. Before, we equipped straightaway booster, but still picking arbitrary routes, which means hole filling order. And now, we can choose routes to get more benefit from the booster. So we can ask a question, which route has the most straightaways? So we asked to the guide, and he said, I'm sending calls to count the exact number of straightaways. That takes forever, so we already asked, so can't you just use a telescope and give me a quick estimate? The guy said, I can't count the exact number, but I can identify routes that definitely have no straightaways. That will work, so at least we excluded hopeless routes, so the racer hope the time decrease. And that's our implementation. HOPE, an abbreviation of whole filling order prediction for efficient synthesis. And matching with analogy, existing booster matches with feasibility analysis, and telescope matches with feasibility scale analysis, which is meta-analysis, which with no straightways matches with whole filling order with no pruning benefit. And we can also figure out when the case all roots have no straightways, we can skip whole feasibility analysis. And let me explain more details. We implemented the algorithm using feasibility scale analysis and whole filling order recommendation, and also implemented new forward-backward abstract operators for the string domain. We support two domain, which is bit vector already at the 2003, and new one for string, which is prefix and suffix domain with length. We also implemented some optimizations like multi-hole simultaneous filling or incremental analysis. Now you must be curious about performance. Yeah, we take the difference with other state-of-the-art synthesizers. Our implementation, HOPE, which is red, gets the best performance. This Sinfonia G is also Sinfonia, which is grammar-adjusted version for fair comparison. This graph is for cumulative time, so the lower line, which is hours, is the best. And for presenting our benchmark as a more general framework, we also tested in other domain, which is big vector domain. Also, in this domain, our implementation, HOPE, took the best performance. And there was a key result. HOPE uniquely solved 76 problems. And now I'll tell you the main idea. I first observed what makes feasibility analysis useless. And then I defined feasibility square analysis that predicts the usefulness, which comes from the first item. And then we should recommend the whole filling order by the feasibility square analysis. How can we do that? Yeah, for each hole, run feasibility square analysis with that hole hypothetically filled. In this concat example, 3 candidates will be there. Yeah, we run for each, and their result in rank 1 to 3. So we see the ranks and recommend which hole to fill first based on results. Let me go into the detail. What does the observation from feasibility analysis? The key observation is, infeasibility is detected when forward and backward results crosses, like even and odd meets and makes a contradiction as both. And another key observation, but never arises from one directional analysis alone. Yeah, it's just a single straightaway program. So if either forward or backward analysis returns top, then analysis cannot lead to pruning. Yeah, let me explain with exact example. These are useless cases. 2 minus whole times holes or 3 minus whole times whole will always produce top, because times whole we can't make constraints as even, but when we pick last hole to fill first, there is the case feasibility analysis result even. So that is not top, so might help cause may not produce top. And let me use this dotted hole notation to denote a hole filled with something unknown but concrete. And now we want an analysis of the analysis that marks these useless cases as must have and might help cases as may not have, which we are interested in. So, jumps to the feasibility square analysis. It is the meta-analysis approach that analyzes the analyzer. Yeah, it's also an abstract interpretation. It predicts how the underlying analyzer will behave when each hole is hypothetically filled. It uses a very simple domain, only may not have, must have, and but. A may not have means the underlying analyzer may return a non-top value, and must have means the underlying analyzer always returns top. By using this simple domain, we mimic the forward-backward integration of feasibility analysis. Forward feasibility square analysis mimics forward feasibility analysis. Hypothetical hole means something filled, so it will be constant, so we result in may not have. And regular hole means nothing filled yet, so feasibility analysis will analyze this as top, so feasibility square analysis will analyze this as must top. In backward feasibility square analysis, whole program will be analyzed by may non-top because it is output, and output is a constant. And other subprogram positions will initially must have and computed by the execution. Yeah, we compute forward-backward pairs to predict pruning potential. And recall, pruning happens when forward and backward meet it and result in both. And then, to recommend hole filling order by this meta-analysis, we do the hypothetical hole filling. Yeah, for example, this concat example has 3 holes, so we just generate candidates with each hole hypothetically filled. First one, middle one, and last one. We perform feasibility square analysis on each candidate. And then we rank holes. Rank 1 holes is some position has may not have and may not have pair. This pair is forward result and backward result. This rank 1 evidence means we may prune the entire candidate. Rank 2s are especially whole positions which has must have and may not have. We can't prune the entire candidate, but we may infer preconditions for components to be filled at that hole. So this might help too. And rank 3 are other ones, no evidence, no pruning benefit. And there will be the admissibility guarantee. We prove this guarantee. If all holes are rank 3, we can skip underlying analysis. With example, yeah, when we use suffix domain in Insight, yeah, we use suffix domain and filling from right will work. Yeah, and in our algorithm, we make each candidate and do the feasibility square analysis. And the first one has no rank 1 or rank 2 evidence, so it will result in rank 3. And middle one has rank 2 evidence. Oh, it's a whole position. So we result this one as rank 2. And last one, which is filling from the right, is rank 1 because it has the rank 1 evidence. The root position in suffix domain, feasibility analysis may analyze this as non-top both directions. So it's the rank 1 evidence. So it has a rank 1 evidence. So entire candidate will be result in rank 1. By seeing this result, we'll pick the left hole to fill first. Let me discuss why this works. It's a very simple domain, just main on top and must tap. Is such a lightweight feasibility square analysis effective? The answer is yes. We balance the analysis cost and guidance quality. Feasibility analysis itself is an already lightweight abstract interpretation, and feasibility square analysis is a further abstraction of the abstract interpretation. And also, it is precise enough to recommend effective hole filling order. And we proved the formal guarantees. And see papers for details, but the key point is soundness and admissibility. Soundness means our feasibility square analysis correctly predicts the underlying analysis behavior. Yeah, we recall, we mimic the forward-backward iteration. And another key point is admissibility. If our strategy predicts no pruning, no other hole filling order can do better. This theoretical provenance is a strong aspect of our paper. With this provenance, and our strategy is also going to existing strategy in synthesizing, you just can adapt this framework to your ones. We did a lot of ablation studies, and let me tell one. This is a time breakdown of our implementation, HOPE. We know that when we get a good result by feasibility square analysis, that will make feasibility analysis more lightweight, but we can see overall result. Just seeing overall result, feasibility square analysis overhead is bearably small in both string domain and big factor domain. So let me conclude it. Battery issue. It's just a conclusion.
Well done. Let's thank the speaker. So we do have time for questions. If people are online, they can submit via Discord. Otherwise, just raise your hand.
Thank you for the great talk. Could you explain in the admissibility proof what you mean by one hole filling strategy being better than another strategy?
So our strategy is not an optimal strategy for hole filling order, but excluding hopeless orders. So admissibility guarantee proves this theorem. That's what was your ask?
I was asking what the definition of better means in the context of hole filling strategies, hole filling orders.
We define the predictable pruning power and define some hole filling orders for math symbols, and we prove that our strategy finds the whole filling order which has least pruning power. When our strategy finds some whole filling order is hopeless, then any strategy should find out that whole filling order hopeless. That is admissibility.
Okay, thank you very much.
I have one. Can you talk a little bit more about how you do this must not true may true analysis? So your feasibility squared. Can you talk a little bit more about how you do that abstract interpretation? Does that work?
Can you speak more loud and slower?
Yeah. Can you talk a little bit more about how you do the feasibility, the feasibility squared abstract interpretation? How do you sort of determine, if a term is a must true or a may not true, or vice versa?
Yeah, in feasibility analysis domain, there will be a top. And in our domain, we have may not top and must top. So we analyze what will be the feasibility analysis result. So must top means the feasibility analysis must result in top. So this has a constraint, but may not top, this is a top of our feasibility square analysis domain. This means no constraint.
And that has to be defined for every feasibility domain, is that right?
Yeah, when it is written in abstract interpretation style.
Are there any more questions from the audience? Let me check Discord real fast. There. Don't see anything. Well, if there aren't any more questions, let's thank the speaker again.